You know that feeling when two totally separate ideas just suddenly click and they reveal a connection you never ever saw before? Well, something just like that happened deep inside the world of AI research. And honestly, it could change pretty much everything. So let's dive in and see what this hidden connection is all about.
Okay, so here's the big question at the heart of all this. For decades, we've had these two major approaches to building AI, and we've always thought of them as completely different things. But what if, on a fundamental mathematical level, they were just two sides of the very same coin?
To really get this, we need to meet AI's two dominant personalities, if you will. I mean, they approach the whole problem of intelligence from completely different angles.
So, on one side, you have associative memory. You can think of this as the brain-like, almost intuitive approach. You see a blurry shape in the distance, and your brain just instantly pulls up dog. It's holistic. But then, on the other side, you've got deep learning. That's the powerful, analytical workhorse of all modern AI. It crunches through information methodically, layer by meticulous layer, to come to a conclusion. So you've got intuition versus analysis.
Let's start with that intuitive side, associative memory. For the longest time, this really amazing idea has been held back by a critical and, frankly, very frustrating limitation.
The classic model for this is something called a Hopfield network. The idea is you give it just a tiny piece of a memory, a partial, maybe even noisy cue, and it's designed to retrieve the full, complete pattern. It's a beautiful concept, right? But in practice, there's a huge catch.
The problem is capacity. Seriously, just imagine a room where you can only have a few conversations going at once before it all just turns into a jumble of noise. A classic Hopfield network is exactly like that room. If you try to cram too many memories in there, they start to blend together, and what you get back are these confused, garbled patterns that don't look like any of the original memories. The network just forgets. And look, this isn't just a metaphor, it's a cold, hard mathematical limit. A network with n neurons can only reliably store about 14% of n patterns. So if you have 100 neurons, you get, maybe 14 memories? That's a massive bottleneck, and it's really limited how useful this entire approach could be.
So how in the world did researchers break through this wall? Well, and this is the really clever part. They didn't just throw more neurons at the problem. They changed the fundamental math. They tweaked what's called the energy function. That's the rule that governs how memories are stored and kept separate by adding in more complex, higher-order interactions. And the result of that one change is, well, it's staggering. Instead of that old linear limit, the new capacity grows exponentially. Just look at that little exponent up there, n-1. This lets the memory capacity absolutely explode. The same network with 100 neurons can now store not just 14 memories, but thousands, maybe even more, all depending on that power n. The memory bottleneck wasn't just solved, it was completely shattered.
Okay, but here's where the story gets really interesting. See, in solving that memory problem, the researchers stumbled onto something much, much deeper, a hidden connection that had been hiding in plain sight for years.
To see it, let's jump back to that other AI mind we talked about, deep learning. This right here is your standard feed-forward neural network. It takes an input, chews on it through some hidden layers, and spits out an output. This is the engine behind pretty much all the AI you hear about today. Seems totally different from that associative memory thing, right?
Well, turns out it's not. And this right here is the big aha moment of this whole thing. The modified energy function, f of x, the one that unlocked all that memory capacity, is the mathematical dual of the activation function, f of x, used in deep learning. To put it simply, the activation function is just the derivative of the energy function. They aren't two different things. They are two different descriptions of the exact same computation.
And believe me, this isn't just some neat math trick. It fundamentally changes how we can think about what learning even is. It gives us a dial, that little variable n from earlier, that can shift the network between two totally different learning strategies.
Let me give you an analogy. When you set that n dial to a low number, the network learns by feature matching. It recognizes a car by spotting its parts. Here's a wheel, there's a door, and windows. But when you crank n way up, it completely switches to prototype learning. Now it recognizes a car by comparing it to a complete, holistic mental image of an ideal sedan. It's learning the whole example, not just the pieces.
And you can literally see this happening right here. On the left, with a low n value, the memories it learns are just these abstract collections of strokes and curves. They're features. But look at the right. With a high n value, the network has learned to store perfect, recognizable prototypes of entire digits. It's the same network, just with a different twist of that n dial.
This chart basically just puts numbers to what we were just looking at. With a small n, a single memory is a generalist. It might help identify a 3, but also an 8 and maybe a 9. It votes for lots of different classes. But crank up that n, and a memory becomes a specialist. Look at that. Over 40% of the memories vote for only one specific digit. They become these pure, dedicated prototypes.
So this is all super cool, right? We have this new learning dial that lets us control how an AI learns. But the million-dollar question is, does it actually make the AI better in the real world? Well, the answer is a resounding yes.
Let's look at the proof. The industry standard activation function that everybody uses, it's called ReLU, corresponds to that n equals 2 feature matching mode. But when the researchers tested a new function based on n equals 3, the rectified parabola, it consistently got a lower error rate on a standard handwriting test. Plain and simple, it was just more accurate.
So the advantages were undeniable. Not only was the n=3 model more accurate in the end, it was also more efficient. It learned faster, hitting its performance goals in fewer training cycles. And maybe most exciting of all, it suggests that the standard tools we've been using all this time are really just the tip of the iceberg. You see, what this research really revealed is that the activation functions we use, they aren't just some random collection of tools. They're all part of a single, coherent mathematical family. The older functions were n=1. The current gold standard, ReLU, is n=2. This new, better-performing function is n=3. This opens up an entire spectrum of new functions we haven't even tried yet.
So this all leads us to one final, just massive question. For years, we've been building incredibly powerful AI without fully understanding what kind of memory it was even using. Now that we have a dial to tune that memory, to shift it from just seeing features to understanding whole prototypes, what new capabilities could we unlock? Could we get better creativity, more robust reasoning? The connection has finally been made, and the exploration, well, it's just getting started.